In this video I want to talk about collinearity or multicollinearity. We earlier talked in the algebra video about matrix rank, which has to do with how many independent columns are there in a particular matrix. And this is a little bit related. So if we have a variable in a data set that can be perfectly predicted without any residuals, any errors, from a set of other independent variables, then we cannot estimate beta. The inverse of x prime x, which is one part of the equation to calculate the OLS beta estimate, doesn't exist, and you cannot proceed. Now this is rare, as in it happens fairly often in applied research, but it happens because of an error in the specification of the model. So if that happens, you just made a mistake somewhere. You need to go back at what went wrong. It does not normally happen in your data itself. Much more common is variables that are highly correlated with each other. Not perfectly correlated, but highly correlated with each other. So I'm not going to discuss the case of perfect correlation. There you just need to change the independent variable so that it is gone. But if you have high multicollinearity, it all becomes a little bit more debatable. So high multicollinearity means high correlation between one and more, between either two independent variables or one and a set of independent variables. So how would you find multicollinearity? So there's a few things you can do. First of all, you can just look at a correlation matrix where you have all the independent variables and look at how they are correlated with each other. That will tell you for each pair of independent variables how correlated they are. It does not tell you whether one independent variable is highly collinear with multiple other independent variables. Another thing that is commonly done is to just take each independent variable one by one and run a regression where that independent variable becomes the dependent variable and all the other independent variables the independent variables. So you regress each independent variable on all the other independent variables, of course leaving out the dependent variable. If you get a high R squared, there is a high linear correlation between the other independent variables and that independent variable, and that means you have a problem of multicollinearity. And finally, the eigenvalues of x prime x will tell you something about the level of multicollinearity. Whether or not this is a real problem is debatable. So there are cases where you can say, okay, these variables are highly correlated with each other, I can leave one out of the model and I reduce my problems. But in many cases there are theoretical reasons why both variables should be in the model, and the fact that they are highly correlated is a simple fact of life. It's not something that we should just obfuscate. And in those cases you need to have a very good argument why you can remove one or not from the model. So you need to think about this theoretically, not just from a modeling perspective. So it's a little bit comparable to a sample size problem. If you have a small sample size, it will be more difficult to detect effects. And similarly, if you have high multicollinearity, it will be more difficult to detect effects. If you have high multicollinearity, you typically need a larger sample size to do your testing. So it does create problems, but it's not always the case that we can simply address it by removing a variable or transforming a variable. We need to think more carefully about is this multicollinearity theoretically important or not? Is it are we trying to separate two effects theoretically that in reality are closely related and therefore hard to separate? Or do we have two or three variables that in a way measure the same thing rather than being just correlated? And would one work sufficiently as a proxy instead of having both? So for example, I might have two variables that both measure economic development, and I am just broadly interested in the impact of the economic development. It might be sufficient to just remove one of the variables and use the other one as a proxy for economic development. But I might also be trying to see the different impact between, say, economic development and corruption, and the two just happen to be highly correlated, but I am interested in the separate impact. I cannot just remove one of the two and not control for that just because I had some statistical problems. If I need a control variable, if there is a confounding effect, which we'll discuss later, then that is an important reason to include the variable and you can't just remove it. But high multicollinearity does lead to some problems in your analysis. So for one, small changes in the data can lead to large changes in estimates because of high multicollinearity. You can get very high standard errors even though jointly these variables are significantly affecting the outcome. In other words, you get insignificant t-tests, but you get significant f-tests. So that makes it harder to interpret. And sometimes the coefficients, they really become unstable, so they can have the wrong sign or be really wrongly estimated because of the high multicollinearity. So with high multicollinearity, the model becomes harder to estimate, it becomes more unstable, it becomes harder to interpret. But the solution really in theory is to make a larger data set, right? To have more observations to address this instability. Or if there's theoretical reasons why you can combine these variables and either make a joint index or remove one and use the other as a proxy, etc., then you can do that. Where you get a real problem is if one is a causal variable of interest, the other is a control variable, and you just remove it because of high multicollinearity. That doesn't work. This is sort of a schematic view of it, so we might be interested in the relationship between x and y are correlated. That is what the overlap means. But the z variable and x are also highly correlated, and then this zone f that you have here becomes a very small amount of covariation between y and x that is still used to estimate the effect of x on y, because this large area G cannot be used to estimate the effect of x on y, because you can't separate the effect of x from the effect of z on y. So to know what the distinct effect is of x on y, you now end up looking at this small area f, and that then leads to this instability in the results. Now we have a matrix algebra equation to calculate the variance of a particular coefficient, right? So we have the variance covariance matrix that we estimate using this matrix algebra. But you can actually formulate this equation in a different way, and I'll do that here just for the purpose of what comes on the next slide. So here we break down the variance of beta hat, the variance of the sampling distribution of our estimated beta coefficient, into a number of components. First of all, the overall variance, so that is the variance of the residuals. So the better the model fits the data, the lower the residuals, the lower also the variance of beta hat. So if the model fits the data better, the residuals are smaller, then also the standard errors will be smaller. The variance of our estimates will be smaller. Secondly, there is this 1 minus r squared underscore k. So this is the r squared that you get when you regress the kth independent variable on all other independent variables. And we already said if that r squared is high, then there is a high correlation between that particular independent variable and all the other independent variables. And that means that there's multicollinearity, and you get a high r squared. So that's in the denominator, and it's 1 minus, so that means if you get a high r squared, you get a lower denominator, you get a higher variance in beta hat. So high multicollinearity means larger standard errors. That is what this says. And then thirdly, the component on the bottom right, that is just about the variance in x itself, and that just says that the more variance there is in x, the easier it becomes to detect whether there's a relationship between x and y, and therefore you get smaller standard errors. But the real point of interest is this part on the left, the 1 minus r squared. Because then we can separate it out. We can say the variance is really sigma squared over the variance in x times 1 over 1 minus r squared. So that is what we call the variance inflation factor. The amount by which the variance in the estimate of beta hat, or the standard errors, are increased because of multicollinearity. So the variance inflation factor is how much is the variance of the sampling distribution of the estimate of beta hat inflated due to multicollinearity. And if that number is high, then we have clear evidence of multicollinearity. We have much larger standard errors due to multicollinearity. If this number is low, this is not so much the case. Now, what is high and low? This is debatable. There's no good rule of thumb. People typically talk about 4 or 6 as high values of VIF scores. So if you have a score that is higher than 4 or higher than 6, depends on which textbook you look at, they will give you different thresholds. You should start to worry. But think about the theoretical reason why a particular variable is in your model. This is more important than a VIF score. Now, I'm not sure there's clear solutions for multicollinearity, and I already discussed some of them so far. So first, if you especially if you have perfect multilinearity, maybe you just made a modeling mistake. Maybe you included variables you shouldn't have included. If you have a categorical variable, you tend to break it down in multiple dummies. If you include all of them, you get perfect multilinearity. You should have left one of them out. Small mistake. The second solution is to increase the sample size, but of course that is in many cases not feasible. If we have data on countries, we can't suddenly create more countries. If we have an expensive survey done and we try to do a regression analysis, we can't so easily just get more cases. But in theory, it's the best solution. If you can increase the sample size, that is your solution. Perhaps you can add one of the collinear variables, but then you have to think carefully about what the theoretical reason was to include it in the first place. We discuss model specification later, and that is really where you don't want to carefully think about. If your purpose is just prediction, not causal inference, then by all means just remove it. If two variables are really measuring more or less the same concept, there might be good reasons to either remove one or, next bullet point, combine the two. But if one is a control variable and the other a causal variable, or they are both important controls, be careful before you remove something from the model. And finally, if you have some kind of reason, mathematical reason why two things should be related, it might be possible to develop a more complicated regression model, not a simple OLS, that explicitly models this relation between the variables.